Yesterday we began deriving functions that kind of looked like this: y equals x to the 3 plus 2x squared, say plus 1. And what we were doing was using the derivative by rule process, or what I call the single term derivative rule, which is that we basically, to get the derivative, what we do is we multiply 3 by the coefficient. Okay, so we've got 3x, and remember we drop that power down by 1. So this one would be 4x, and remember the constant cancels out because the derivative of a constant is 0. So today all we'll do is extend the variety of functions that we can derive, because remember what we're doing when we're deriving is we're producing the gradient function. So given the function is f of x, what we get with a derivative is f dash x. This is the gradient function. So if our function is written with a rational power, or it's written with a negative index, it'd be nice to also be able to derive that. For example, a function that would be written with a negative power is, for example, 1 on x squared. Remember that, that's the truncus, okay? So that's that function there. It'd be nice to be able to derive that. But how do we get a derivative in this case here? Well, what we're gonna do is express this with a negative index. So if we write this as f dash x equals x to the negative 2, once it's written like this, we can just use that same rule that we've been using, or that we were using in the last lesson, which is we go negative 2 multiplied by 1 and then drop the power by 1. And it's the same with rational indices. Like in year 10, a student asked me the other day, what's the point of writing the square root? So if we were square rooting 9, what I said to her is that's the same as 9 to the half. And what she was asking is basically, what's the point of writing it like that? Why can't we just leave it like that? Well, again, what we can do is once we explore the square root function, that is y equals root x, if I can write it as y equals x to the half, I can also use the same rule, half multiplied by the coefficient, drop the power by 1, to get dy dx. So these two rules here are all about extending the kind of function that we can derive to get the gradient function for. So let's just try it out on a half dozen examples. So we've got y equals this, so our notation is going to mean that we're going to use dy dx. Alright, so what we do is we grab this index and multiply it by the 4, so you just got to be good with your directed numbers, x, and the power drops by 1, so that's going to go to negative 3. All right, now I tend to, when they're all positive, just put the plus straight there, but now the sign of this is going to be dictated by the index here. So this is negative 1 multiplied by positive 5. That's going to be negative 5x to the negative 2, and the constant drops. Now, typically what we do with the gradient function is we end up substituting a value in. So it's usually good practice, not necessary in this case, but good practice to write all of your powers with positives on it. So I'm going to rewrite this as negative 8 over x to the 3. So I'm using that negative index rule. Take away 5 over x to the 2. And that means that if I was substituting a value into dy dx, it's just easier than trying to evaluate a negative index in your head. Okay, so this one here, what we're going to do is, this is the problem index here, okay, because it's in the denominator. So what we're going to do is just bring it up into the numerator, make it negative, and then use our single term derivative rule. So I'm going to write y equals 2, x to the negative 3, take away 6x cubed. And note that I haven't broken into the derivative yet. I'm still saying that this is a rewritten form of the original function. Okay, now I'm ready to derive, so I'm going to go dy dx equals negative 3 times 2 is negative 6, x to the negative 4, take away 3 lots of 6 is 18, x squared, and again, it's probably going to be useful to write that with a positive index. Not necessary, but if we have to evaluate it, it becomes handy if it's written positive. Okay, how would you begin to derive this one here? Well, what we've got to do is we're going to divide both the terms in the numerator by the denominator. Okay, so this is the same as saying y equals 2x to the 3 over x, take away 4 over x. Okay, so all we're doing is we're kind of splitting the denominator between the two terms in the numerator. All right, now what I can do is rewrite each of these. I'm going to rewrite this one as 2x squared because that cancels with that. And this one here, I'm going to bring that x to the top and write it with a negative index. So that's take away 4x to the negative 1. And now we're ready to derive. 2 times 2 is 4x. Now this is going to be negative 1 times negative 4 is positive 4x to the negative 2. Power goes down by 1. And again, we'll just clean up our derivative a bit. 4 over x squared. Okay, this one here will be exactly the same process. So what we're going to do is, before we break into the derivative, what I'm going to do is split the x squared between the two terms. Okay, now what we'll do is I'll simplify each of them. So that becomes that, and this becomes that. So that's plus 2 on x. All right, now this is the problem. So what we're going to do is grab that x and bring it up to the numerator. Okay, derivative time. Okay, derivative of x is 1, so it's going to be 1 times 1 is 1, x to the 0, so that's going to be 1. And then we've got negative 1 times positive 2 is negative 2, x to the negative 2. And finally, we'll just clean that up. There it is there. Okay. All right, so some rational indices. So again, what we're going to do is rewrite this. So we're wanting to find the derivative of this, but we're not too sure how to do it. Well, again, if it's got an index, then I can use the single term derivative rule. So I'm just going to rewrite this as y equals x to the half, and now just use my rule. Okay, so I'm just going to go half of 1. So dy dx equals a half times 1 is a half, x, and I've got a half and I'm dropping it by 1. So a half take away 1 is the same as a half take away 2 on 2, which is negative a half. You'll get used to doing that one. Okay, so let's clean this up. So what we'll do is this could be written x to the negative half over 2 like that. So I'm just multiplying this by the 1. And then all I'm going to do is use the negative index rule to grab this and chuck it into the denominator. So that's going to be 1 over 2 x to the half. And I can go even further than that and write it as 1 over 2 root x. Okay, so there's my derivative function. So the derivative of this, the gradient function of this, is this. All right, same process with this one. That's x to the 1/3 dy dx equals. All right, so we've got a third of 1 is a third x, and we're removing 1 from a third. So from a third, we're going to remove 3 on 3, which is negative 2 on 3. Okay, let's clean that up. So that's going to be 1 over 3x to the 2/3. And again, doesn't really have to be done, but we'll go 3. So I'm going to go x to the 1/3 to the 2. And then finally 1 over 3, third root of x all squared. Okay, couple more. Okay, this one here, I'm just going to rewrite this as f of x equals x plus 2 over x to the half. Now I'm going to split the denominator. Okay, now what I've got is common base indices being divided. And what we do is we subtract the powers. So that's f of x equals x to the half. Okay, so 1 take away a half is a half. Then this one I'm going to rewrite as 2x to the negative a half. Okay, derivative time. So f dash x equals, so this one's going to be a half x to the negative a half. Let's make a mistake there. This one is going to be negative times a positive is a negative. 2 lots of a half is 1. So this is going to be x to the negative 3 on 2, because negative a half take away another 1 is going to be negative a half take away 2 on 2. All right, so let's finally clean this up. We've got 1 over 2 x to the half plus 1 over x to the 3 on 2. That's going to be 1 over 2 root x plus 1 over root x to the 3. All right, last one. So this one here, what we need to do is expand the perfect square first of all. So we're going to go g of x equals. Now when we expand the perfect square, remember what we do is we square the first. So that's going to be x. We do 2 lots of this times this. So it's going to be 6 root x. And then we square the last. So it's going to be plus 9. Okay, now what we want to do is get a derivative for this. So we're going to go g of x equals x plus 6x to the half plus 9. Okay, we've got it all in the single terms now. So g dash x equals derivative of x is 1. Half of 6 is 3. X to the negative a half. Constant drops. G dash x equals 1 plus 3 over root x. Pretty cool. So what we've done today is basically just extended our repertoire of things that we can get gradient functions for, which is fantastic. So we were a bit limited by kind of the more polynomial type deal yesterday. So anything that was polynomial we could derive, but we've already extended that today. So now we're non-polynomial here, and we can already derive rational and negative index, things like truncuses and hyperbolas and all sorts of things like that we can now get derivatives for. So give these questions a go. There's not too many there, and I'll catch you guys on Monday.